Hello, my name is Ben Taylor. I am CTO and co-founder of Rainbird Technologies. Thank you so much for inviting me along to talk to you today. It's a real pleasure to be here. Now, I've been in the field of AI for something like 25 years. I sometimes joke that I studied AI back in the 1990s, the last time it was interesting. It seemed to go in these funny kind of cycles of summers and winters, and we're certainly in a red hot summer for AI right now. Now, Rainbird is a decision intelligence platform powered by Neurosymbolic AI. And that's what we're going to look at in this talk. We're going to look at Neurosymbolic AI. We'll look at the neuro, we'll look at the symbolic, and we'll look at some of the strengths and weaknesses of those two different approaches. But then we'll look at Neurosymbolic AI and how combining these two worlds can deliver a technology that is greater than the sum of the parts. Now, some of you may have been to my colleague James Duez's talk, A Hitchhiker's Guide to AI. Now, in that talk, he framed some of the way that we see the world and some of the challenges that organizations are facing around implementing these technologies in this red hot summer of AI that we find ourselves. So I thought I would start by just touching on some of the themes that James picked up on and reiterating some of those points, because that's an important part of why we're all here. I think we must recognize that every organization is starting to see the transformative potential of generative AI and large language models. But as they start to look to how they might apply them in their organizations, we're all starting to see the significant limitations. And these limitations include the tendency of these models to hallucinate, that is, make things up, and actually the inability of a large language model to explain itself. We can think of large language models as enhancing the user experience of experts, but we cannot, or at least we should not, be delegating decision making to them. And when we've been looking at this, we've kind of observed that the world is divided into two very different camps, almost two disparate planets, if you like. So on the one hand, we've got lots of people maybe living on what we might call planet data. These are people who are totally focused on machine learning and what can be done with it. And we've had an absolute fascination with data for the last couple of decades. And actually that is for very good reason. A lot of economic value has been driven by insights and predictions that can be made over data by people sitting in this world, this planet data world. But there are big challenges. We are definitely in a hype cycle right now, and expectations for large language models are very high. We're going to look at how large language models work in just a second, and you will see that they are predictive machine learning machines. But we have to recognize that the outcome of those machines, the outcome of machine learning tools in general, are predictions, not judgments. I'll talk about that some more later on. And of course, you can't build these models at all if you don't have data to start with. We all understand perhaps that bias and explainability are definite factors in being able to deliver value from machine learning models. So there's a lot of people in Planet Data who are trying to close this gap between the data that they hold and the ability to go and take action on it. So then over on the other side, we have Planet Process. And people living on Planet Process are really trying to automate things. They're trying to take existing processes and automate them and make them go faster. And again, there's lots of value in automating simple things, but actually when those processes or maybe decisions become more complex, these kind of linear processes, workflows, decision trees become too simple. They fall down very quickly. We're hearing from the analysts that robotic process automation is dead or at least dying. We find that tools like process mining to uncover the underlying processes deliver diminishing returns as actually trying to automate the more complex things that they find fall foul of this tendency for linear, simple process systems to fall apart. So the result is that we build these processes that are very limited, they're brittle and they're difficult to maintain, but yet people on Planet Process have similar aims to people on Planet Data. They want to extend their automation agenda to include more complex, more human-like decision processes. And so they meet in the middle, these two worlds. They meet in the middle in their desire to bring intelligence automation to human decision making. And this is where Rainbird sits. And this is what decision intelligence is. Decision intelligence is a gravitational force which is pulling these two planets together. Now we're using decision intelligence to automate complex, situational, human-centric decision making. And we do this by leveraging knowledge graphs, large language models, neural networks. And actually, the technology that underlies what we are is neurosymbolic, which is what I'm going to talk about today. One last note on AI and this red-hot summer that we find ourselves in. I'm sure we're seeing similar things said all over the place. There is this incredible and almost unlimited budget and this overwhelming excitement and this huge fear of missing out that we're seeing around AI right now. But it's very important to remember that we must connect what we're trying to do to the outcomes that we're trying to seek. We must make sure that we keep the business problems we're trying to solve front of mind when we're deploying these models. But AI is a broad church with a long and rich history, actually going right back to the dawn of digital computing. So when we say AI, we really mean any one of a large set of different kinds of technologies, all suited to different kinds of challenges and different kinds of situations. We're going to look at a few today so that we can start to define what we mean by neurosymbolic AI. So let's look at a few key terms. So first of all, there's machine learning. Now actually, a bit like AI, machine learning is also a broad category. It's quite unhelpful really because it's not any one thing. It is also a broad set of different kinds of techniques that you might apply to data. We can really describe the machine learning as any system that is using data to create algorithms but without having to explicitly encode or develop those algorithms. Really, machine learning is about using data to identify patterns or make predictions. We're going to talk a lot more about predictions later on. And then there's symbolic AI. Now, symbolic AI is a term that's having a bit of a resurgence at the moment, and it's kind of almost the opposite of machine learning. It does have to be explicitly programmed. It works in much the same kind of way that we might teach people. Actually, a lot of people forget their AI history, and actually symbolic AI was huge in the 1980s and 1990s, with governments putting billions and billions into research and development around symbolic AI. We're going to have a little look in more depth at symbolic AI in a little while. And then I've also chosen to pick out generative AI here. Generative AI I would class as a kind of subcategory of machine learning. And these are algorithms that use huge data sets at unimaginable scale to be able to generate some kind of output. Of course, the one that we're all very familiar with is ChatGPT, because that's what kind of triggered this current AI summer that we're all in. We'll look more at particularly large language models and GPT and how they actually work in just a moment. I absolutely love this cartoon from XKCD. It's quite old, but it's actually still just as relevant today. I think it's important to understand that when we're talking about machine learning, this is really what we're doing. It is extremely difficult to take a machine learned system and ask it why or how it's made a particular prediction. And that gives us this gap between data and this ability to go and take action on data. And we'll talk about the difference between prediction and judgment in just a moment. Okay, so I said we'd talk about large language models and how they actually work. I think given all the excitement that there is around ChatGPT, and actually GPT being the leading approach to making large language models work, it makes sense to look at the GPT architecture and what's really going on behind the scenes here. So GPT, what actually is it? Well, the clue is actually in the acronym GPT. Let's break this down for you and see what this is really doing. The G in GPT is for generative. So that means that this is a system that is designed to generate output. It's really trying to predict words that should come after a particular sequence that you've given it. Again, we're going to talk about prediction later on, but it's important, I guess, to think of GPT like a word guessing machine. I've heard people talk about GPT as being like autocomplete on steroids. So the P in GPT is for pre-trained. Really, that means that these are models that have been trained on a huge corpus of text, typically scraped from the open public internet. The key thing to understand here is that these models have been intended to be trained once, but then used in a large variety of different situations. So they're not trained on your expertise, they're trained on text that it's scraped from the open internet, such that it can go and understand language. They're phenomenally good at understanding language, but can also be deployed into lots and lots of different and diverse kinds of situations. And then finally, the T is for transformer. And transformer is the actual architecture by which these systems are able to make predictions about which words should form a completion, should form the next part of a sentence, or any kind of output that these things are generating. So we're going to dig into the transformer architecture and what's actually going on behind the scenes in a transformer architecture. These systems are really using neural networks, a form of machine learning technology, and really our task in building a transformer is to use a neural network to predict the next word that should be included in whatever output it is that we're generating. But we have a challenge here, and that challenge is that computers, as we know, work very well with numbers. They're number crunching machines, but they're not so good with symbols. Computers don't really understand words or tokens or pieces of words so well. Certainly not if we want to go and do mathematics on them. So we might be able to use a computer to show very easily a mathematical statement, but would struggle with the trying to calculate mathematics or understanding of words themselves. So the way that we solve that is by using a technique called word vectors. And word vectors actually enable us to go and do the latter of these two descriptions that I've got on the screen here, allow us to go and do mathematics over words themselves. So very briefly, what are word vectors? Word vectors are really just a list of numbers. You can think of a vector as just a big array, so it's a great long list of numbers. In a large scale system like GPT-4, those lists of numbers might be very, very long, a large set of numbers, although there are models that use much smaller vectors. And really, a word vector is a large list of numbers that represents a word. This is actually an example of a smaller vector that was generated for the word cat. There's a nice picture of my cat there. For the word cat, this is the vector that might be generated by learning those numerical representations based on how that word appears in a corpus of text. In this particular example, that's by understanding how the word cat appears in Wikipedia. Imagine if you scale that up to something where you've got much more text input, we can start to learn a numerical representation for the word cat based on the way that it appears in the open public internet, the way that people are using and understanding that word. So what we do is we use some quite clever techniques to go and learn a numerical representation for every word that we might encounter, building a huge vocabulary of these word vectors. Now, the actual individual numbers that make up a word vector, we don't really care too much what they represent. In fact, because of the techniques that are used to learn those word vectors, we don't even really know what those numbers individually represent. But we do know that we can do mathematics on vectors. We can compare one word with another, for example, and see how similar they are by how close those two different vectors are. We can do mathematics on these numerical representations. Now that suddenly becomes very powerful because now we have mathematical representations of words that encapsulate something of the meaning of that word in the context of the way that it is used in our training data in this huge corpus of text that we give these things, such that we can make predictions about how that word should appear in sentences and what it might mean when it appears in a sentence. But actually we need a little bit more than that. Context is really important in the way that we understand language. Take this sentence, for example. The customer asked the mechanic to fix his car. If I give you that sentence and I ask you the very simple question, whose car is being fixed? For most of us, it's pretty obvious that it's the customer's car that is being fixed. But in understanding that it's the customer's car that is being fixed, when we refer to his in the sentence, we mean the customer. Really what we're doing is applying our own understanding of these words. We understand that a mechanic is somebody who might go about fixing cars, so it's most likely that actually the customer is asking the mechanic to fix his car rather than the customer asking the mechanic to fix their own car. That idea of context is really, really important. Transformer architectures include a mechanism which we call attention or self-attention. Really what this allows us to do is to start to understand through training the way that a particular word relates to other words within a sentence. We do this by modifying each word's vector so that it carries some of the context of its situation within a particular piece of text, within a particular sentence. So the word customer and the word his, we might actually inherit a little bit of that word vector for customer into the word vector for his, such that the understanding of what we mean by his in this sentence is mathematically shifted slightly. This means that we're now able to make better predictions about what might come next. If I included the sentence whose car is being fixed, we might make a better prediction that it's the customer's car being fixed because the word his has inherited something of the vector space that describes the customer. And actually the way that this works in transformers is we do this over and over and over again. That we have multiple layers that we pass this through. Actually, in something like GPT-4, at very, very large scale and at great cost. We need a reasonably large amount of computing grunt to be able to go and perform these tricks, to be able to make us understand a sentence so that we can go and predict the next output. And of course, technologies like GPT-4 don't just work on single sentences, they work on context windows that are much, much bigger, that can understand the context of individual words, can pay attention to those individual words' context within a large corpus of text, so that we're able to make really much better predictions about what should come next at the other end. So this sounds like magic, and it is very, very powerful, but there are some things to watch out for. It is very important to remember that large language models really are word prediction machines. Large language models are trained on text from the open public internet. So you've got to think of an LLM as really its task as being to produce the output, to predict the text that is most likely to appear on the open public internet. So you kind of get this medium output from anything that you're asking for out of GPT-4. You're not going to get it to produce output which is specifically trained for your corpus of data unless you go and fine-tune or build models yourself. These things are just machine learning models. They don't have any sense of core beliefs or know right from wrong. They don't understand facts. As a result, they often make mistakes. They make mistakes where maybe their training data was inconsistent, or actually their attention is wrong, where they don't attend to the right output, the right parts of the text that you've given it. A good example of this is seeing how bad most large language models are at mathematics, particularly mathematics that includes big numbers. The reason for this is that they haven't got a whole load of big numbers in their training data. There are lots and lots of small numbers in text that it's scraped from the open internet, and so it does quite good with numbers that are smaller, but it doesn't do so well with large numbers. You can try it yourself. Go and ask ChatGPT to do some mathematics on some bigger numbers and then validate the output with a calculator. You'll find more often than not it gets the answers wrong. Incidentally, it seems that large language models have a particular liking for the number 42, which, as a callback to James's talk, is a number which is referenced very often on the open internet. It's also important to understand that large language models are autoregressive. If you think about this process, they guess the next word, and that next word becomes the input for the next round of generation. Well, actually, errors accumulate very quickly across the way the model works. So when these things start to deviate and start to go wrong, they go wrong very quickly. I said I would talk about the difference between prediction and judgment. I'm hoping that you're starting to see that what large language models do is make predictions in their output. But we would argue that prediction and judgment are really not the same thing at all. In order to make a decision that you can take action on off the back of a prediction, it requires a human expert to apply a layer of judgment. You need to apply your own expertise to some kind of a prediction in order to go and make that into a decision that you can take action on. So typically a large language model might produce output that you then need to give to a human expert to go and validate, to apply their own layer of reasoning and judgment to turn that into something which you can actually go and really use in the real world. A lot of the output from large language models can look convincingly right and be completely wrong, or be wrong and actually be right. You can ask a large language model for an explanation for its answer, but actually what you get, of course, is just a prediction of an explanation. It is not a chain of reasoning. It is not judgment. And you can see this actually in GPT itself. Those of you who have played with ChatGPT will be familiar with this little box down at the bottom here, where they're being quite open about the fact that it might produce inaccurate information about people, places, or facts. You cannot rely on this technology anywhere that you're trying to go and make decisions. And actually, there are a whole bunch of other risks. Some of these are quite poorly explored. There's a big groundswell of change in regulation, particularly coming out of Europe and other territories, which is looking to address some of these things. But if you're trying to use any kind of machine learning technology, particularly large language models, you have to be alive to the fact that there are challenges around fairness, there are challenges around bias, and particularly intellectual property. There are class actions being raised right now against some of the large organizations who are gathering information from the open internet to consume into these models, whether that's a large language model or some of the diffusion image generation models. We have to answer questions about privacy and security. This idea that an explanation from these models is a prediction, not an actual explanation, that makes explainability, even though it can look very compelling, still quite challenging. We don't know that these systems are producing reliable or accurate output. A lot of questions need to be answered within your organizations about what kind of impact these tools are having on the way people are working. And of course, there is great environmental impact to the massive compute that these tools require in order to go and deploy. In fact, what I was reading in the press just recently, that the current prediction is that AI, by which I think we probably mean large language models, is likely to take the energy requirements of a small country within the next 2 years. So there's definite environmental questions to answer about our use of these technologies. And of course, there's risk of reputational impact when these machines get things wrong. But despite all of that, everybody wants to use them. I think we're seeing something not all that dissimilar to the sudden rise of mobile apps some years ago, when everybody wanted to have an app, but we didn't really know why or for what purpose. We're seeing the same thing here. We must use ChatGPT in our business, despite an understanding of all of the risks and all of the challenges, but we do know that we want to go and adopt these technologies across the business as quickly as possible. So what's the answer? Well, this was our hypothesis when we started Rainbird 10 years ago. Our hypothesis was that actually the world does need AI that it can trust. And we see that now more than ever. Actually, with this growing demand for these kinds of technologies, we know that people need to have trustworthy AI. And by trust, I mean AI that is explainable, that can be absolutely reliable, and is traceable, that we can see the reasons for the way these machines have made their decisions. And that brings me on to symbolic AI. So what is symbolic AI? Well, as I mentioned, it's a term that is starting to have a bit of a renaissance. We're starting to use this term again. I think you'd be forgiven if you're new to AI for thinking that AI is all about data. But actually that's not true. In the 1980s and 1990s, AI was really all about knowledge. And that knowledge came perhaps from interviewing human experts, which was then captured into symbolic AI systems. And despite all of that history, actually symbolic AI has a rich history. It received so much attention in the past, probably as much attention as these data-centric approaches receive today. Projects received research funding, received billions of dollars in government funding into research and development of these systems, both in the US, in Europe, and in Japan. But despite that, this human-centric approach has not really been discussed much in recent years. Symbolic AI is really all about starting from knowledge. Actually, just like machine learning, this approach represents an alternative to creating computer software by writing code. But unlike machine learning, the source of knowledge for symbolic AI systems is human experts. That might be through them sitting down and being interviewed by a knowledge engineer and their expertise being encoded, or maybe them sitting down in front of a system and building models of their own expertise, how they understand the world, directly into a system. And a great advantage of symbolic AI is its ability to explain the answers that you get when you ask questions of these models. Because we're starting from models of human expertise, we're starting from explicit and formal representations of the way people really go about reasoning about making decisions in their world. We're also able to go and show how we reached those decisions. It solves very neatly the explainability problem. So you might be wondering, if this is a super powerful approach to solving these problems of explainability and so therefore problems of trust, if this would allow us to go and deploy these systems into complex environments where we actually want decisions that we can take action on and so therefore require trust, if this allows us to deploy models into regulated environments, why isn't symbolic AI something we're talking about all the time? Why isn't symbolic AI the mainstream approach to solving these problems? Well, as machine learning has trouble with explainability and bias, symbolic AI has a problem too. And the core problem with symbolic AI is called the closed world assumption, or the closed world problem. Now, the closed world problem is quite easy to understand. When you think that a symbolic AI model is all about capturing human expertise, actually these symbolic systems only know what they've been taught. Their domain of expertise is limited to only what you tell it. If you try to ask questions outside of what has been encoded in a symbolic AI model, it won't be able to answer those questions. It is very hard to transfer learning from one part of this symbolic world into another adjunct or different domain. And this closed world problem becomes particularly true when you're trying to describe something that's very, very big. Symbolic AI works well in particularly discrete and well-defined domains, such as tax or professional services. But if you extend that out to something which is much bigger, say, for example, healthcare, imagine trying to model all of a clinician's expertise and 7 years at medical school into a system where you're having to interview that expert on absolutely everything that they know. Well, this becomes an intractably large problem of scale to be able to build these things into symbolic AI systems. So we have these kind of two disjoint approaches. On the one hand, we have machine learning with all its power of prediction over data, but its trouble with not being able to explain how it came to a decision, and so a gap and an inability to go and take action on the predictions that are made by machine learning. And we have symbolic AI with its power to be able to explain its reasoning, to be explicit in why and how it's made an answer, but suffering from the closed world problem, which locks it out to bigger, broader use cases. So what's the solution? Well, the solution is neurosymbolic AI. Unsurprisingly, neurosymbolic AI is really taking the best parts of machine learning, particularly in neural networks, and the best parts of symbolic AI to allow us to ground the decisions that are being made by machine learned systems into delivering something which actually is more powerful than both of these approaches individually or combined. Neurosymbolic AI is actually quite a broad field, and there's lots of different approaches to neurosymbolic AI. As I say, it's really about combining neural networks and symbolic AI, but it's really about bringing tools for symbol manipulation, which is really what symbolic AI is all about manipulating symbols that describe our world into the abstract world of machine learning. So we're taking concrete models of knowledge that we build in the symbolic domain and combining them with this kind of abstract and fuzzy experiential world of machine learning. Now, there are lots of different approaches to achieving this aim of combining these two worlds, and there's been research for many years in this field. Many of you will be familiar with some of these. You'll be familiar perhaps with AlphaGo. AlphaGo that initially beat Lee Sedol at the game of Go was a neurosymbolic approach. We're using Monte Carlo and various other techniques alongside machine learning to deliver that system. You can think of ChatGPT as machine learning, as I've just described, but for those of you who maybe have played with ChatGPT plugins, you might be aware that you can bring in some of the computational and symbolic reasoning capability of Wolfram Alpha. So you can have ChatGPT go and interpret your query and turn that into something that's structured for Wolfram Alpha to go and make a computational recommendation, a decision, or do some mathematics. I said that GPT is very bad at performing mathematical calculations, and it absolutely is, but it is very good at understanding that we can pass this off to some other machine like Wolfram, which is able to, combining these two different approaches. There's a lot of research undergoing at the moment about using knowledge graphs, and I'm going to talk more about knowledge graphs because that's what Rainbird is in just a second, but using knowledge graphs really to ground large language models in reality, so that you can tie the answers that you get from something like ChatGPT into something which is knowledge based, which is actually backed by something which has its roots in human expertise. And there are many other approaches. I'm going to introduce the Rainbird Neurosymbolic approach to you today. One thing to think about these different approaches is that these are really composite approaches. And there's a term which is starting to arise, which is Composite AI. Composite AI is really about taking an approach that uses multiple different models to enable us to broaden the applicability of what it is that we're building, to broaden the decision space that we're exploring. The composite AI is not necessarily the same as neurosymbolic AI. There are composite approaches that don't include any elements of symbolic AI, but you can think of neurosymbolic AI as a kind of composite AI. And actually, some of these things are being written about by the analysts. I'm sure you're all very familiar with the Gartner hype cycle that shows where different technologies might be delivering different kinds of value over the next few years. I think it is absolutely fascinating to look deeper into some of the Gartner's research. And we can see that they are including decision intelligence, which is the field that we would consider Rainbird working in, and composite AI actually in the same box as generative AI, as having transformational impact over the next 2 to 5 years. Now, you will see also that they're putting neurosymbolic AI as having high impact over perhaps a longer time frame, but actually some of these things can be delivered today, and we would argue can actually add significant value right away. These technologies are here now and are usable immediately. So what does neurosymbolic AI look like in practice in a platform like Rainbird? Well, Rainbird is all about knowledge graphs. At the center of our world is a knowledge graph that describes all of the concepts that exist in your world and how they relate to one another. It is this knowledge graph that we reason over, we connect to data, and we ask questions of. I'll give you an example of how that works in just a second. The best way to understand neurosymbolic AI in the context of Rainbird is to walk you through a typical AI model lifecycle in Rainbird. And this typically takes maybe 6 different steps, starting from building these models all the way through to deploying them to the outside world and letting the outside world interact with them. So we start with build. Building in Rainbird either starts from a human subject matter expert sitting down in front of our no-code studio and building a knowledge graph that describes their world by hand, or giving the system documentation from which we can extract one of these knowledge graphs. So we can build these models starting from documentation. This starts to open this closed world box that has hampered symbolic AI for all these years, because we're now able to give these systems large amounts of data, large amounts of documentation, and have the system automatically produce symbolic models for us from our documentation. Of course, the human subject matter expert is very important in this process. So once these models have been built, you then go through a process of refining your model. That might be the human expert looking at what has been built, looking at these knowledge graphs that have been built, and making decisions about how they might do things differently, or maybe they might add some of their own expertise over the top of what has been extracted or what has been already built. But data has a role to play here too. You can build these models with no data at all. We solve for the data availability issues of machine learning because this is a neurosymbolic model. It doesn't start from data, it starts from expertise. But if you have historic data, at this refined step, you're also able to introduce those data to Rainbird and have it make recommendations for you for how your model could be improved. Maybe there are relationships that you missed in your model. We're able to surface those from the data that we're seeing to further refine your model. This goes further to opening up this closed world assumption, allowing these models to be refined from data to learn from experience. Of course, Once you've built and refined your model, you're then going to want to see how well it's performing. So we provide a set of quite advanced test tools that allow you to design your own tests, to build regression tests, to protect your models from regression over time, but also to validate that these things are performing in the way that you would be expecting them to perform. As with any large enterprise piece of software, you would expect we have a big set of model ops tools that enable and ensure smooth and safe deployment of your models so that you can monitor how well they're performing, you can collaborate with other authors and control versions and all of the things that you might expect from managing models in production. Now, once you've deployed these models, you're going to want the outside world to interact with them. Now, you might be doing that in a structured way. You might be saying, I've got these structured data or these structured queries that I want to pose of this system in order to solve for some kind of problem. But of course, that's quite a closed world way of thinking about things. We're opening the closed world. So you're also able to present queries in natural language or data either that's unstructured or in natural language, or data that doesn't necessarily match the knowledge graph or the ontology that you've designed, that you've built and refined in Rainbird. We're still able to go and make inferences over those data that you give Rainbird, even if it doesn't exactly match this model. And then, of course, once your model's in deployment and people are starting to interact with them, you may be giving feedback on the decisions that Rainbird's made. And actually, in a technically very similar way to what we're doing in the refine step, if you're refining these models from data, you're able to take that learning, that feedback that you're giving these models, and use that to strengthen the knowledge graph that you've built, to make recommendations for how this graph could be made stronger. At the center of all of this is the Rainbird Engine. And the Rainbird Engine, it really consists of three different parts. So let's just dive quickly into the three parts that make up the Rainbird Engine. As I say, at the core of everything that we do is our extended knowledge graph. So the extended knowledge graph encodes all of your expertise, all of your understanding of how decisions should be made in your organization. Now you connect these knowledge graphs up to data, and then you can start asking questions of them. You can run queries. And those queries are processed by our reasoning engine. And the reasoning engine is a symbolic AI engine. There is no machine learning, no language engine, no risk of hallucination in the way that our reasoning engine works. The reasoning engine is reasoning over these formal, structured knowledge graphs along with data, albeit within degrees of certainty. But that means that every answer that you get from the system comes with a fully auditable chain of reasoning that describes exactly how a decision was made, all of the data that was considered, every step that we took in coming up with a particular decision. This is very different to using a large language model or machine learning to drive a decision. This is fully explainable. This means that you can get a decision that you can actually go and take action on. Alongside the knowledge graph and the reasoning engine, we have two other parts to the Rainbird system. We have a neural engine. So the neural engine is actually how we go about making recommendations to you for how you might improve your knowledge graph. This is analyzing your graph. It's using neural networks to analyze your data to make decisions about recommendations that we could give to subject matter experts for how these graphs could be made stronger over time. Then alongside this, we have our language engine. And actually the language engine has two functions. First of all, it's there to take documentation that you present to the system and extract one of these knowledge graphs, along with all the weights and certainties and rules that there might be in your documentation that you give it. But the language engine is also responsible for providing a natural language interface with our reasoning engine to allow you to ask questions in natural language, but also to allow you to present data to the system that doesn't necessarily match what has been described in your knowledge graph, so that you can use these graphs in multiple different situations, so that you can transfer that understanding that you've built into other adjunct domains and continue to benefit from these models that you've built in Rainbird. So look, I hope I've given you a little bit of food for thought here. I hope I've started to open up some of the mystery that surrounds some of these different technologies and maybe introduced a new approach to you. If you're interested in finding out more, we're here with our booth. Do come over and come and say hello. Very happy to come and give you some examples of how this works in practice, or do get in touch using the details that are on the screen. Thank you for your time.